Good day, ladies and gentlemen. You are all welcome to our lecture number 5 on Cmen843. Today we are going to continue on or to start looking at electrical properties of semiconductors. As we all know, the reason why semiconductors are developed is for them to be used in electronics, where conduction of electricity is needed. Now, we also know that whenever an energy is applied to a semiconductor, the conductivity will start. And this energy can be electric energy, it can be heat energy, sometimes it can be light energy. So in that case, whenever an energy of magnitude E is applied to a semiconductor device where the band gap energy, Eg, is given, then we should have density of electronics, that is concentration of electronics in the semiconductor, and that is given by Z of E equal to C subscript E into E minus Eg all raised to power half, that is a square root, where this Eg is the concentration of the electronics, the electrons. Let's differentiate between this. This is density and this is concentration. The density means per unit volume or per unit area, but the concentration, it means the number in the whole semiconductor material. So this Ce is given by this 4 pi into 2m asterisk subscript E raised to power 3 over 2 all over h cube, where Me is the effective mass of electron and h is the spacing, the distance between the conduction band and the valence band. And the density for hole, the one we have just seen here, is that for electrons, while that of hole is given by similar formula, but here we have Z of E equal to CH instead of CE, and in the bracket we just have minus E. The Eg is not involved, square root or raised to power half. And the same thing, this CH is the concentration of the holes, which is given by similar formula, that is 4 pi into mH asterisk raised to power 3 over 2 all over h cube, where we define h as the spacing. Now, this issue of concentration of either holes or electrons, this figure number 1 is telling us that the concentration of electrons or holes exist in only allowed bands. We know in any semiconductor we have 3 bands. We have the valence band, we have the conduction band, and in between them we have what we call forbidden band. So this graph is showing us that the electrons are rising exponentially if you look at it, and they are within the conduction band, and the holes on the opposite side, they are in the valence band, while the region between the two is the forbidden band. And you can see that all these two curves, they don't exist within that limit, which means we don't have concentration of holes or electrons in the forbidden band. They exist only in conduction band for electrons and valence band for the holes. So if you want to obtain the total number of electrons that exist in a particular place, because what we have seen is the density, that is the number of electrons per unit area or per unit volume. But now if you want to get the real number of electrons, we have to use this formula, which said Ne, that is the concentration of electrons, should be the integral of the density of states times the Fermi function we have seen before, and this integration is done within 2 limits, from the bottom of the conduction band to the top of the conduction band. But this integration we have just seen, this one here, it has some problems that will make it very difficult to be evaluated. One of them is the solution for this density of states is only valid at the bottom of the band, but our integration is between the bottom and the top. This is one of the difficulties. Another problem that will make it very difficult to be evaluated is the Fermi function, which we know is given by formula like this, and it is not suitable, it is not easy for analytical integration. And also the third problem that will make that integral very difficult to be evaluated is the fact that we need one more parameter in order to include the width of the conduction band, because you can see the limit we have is between the bottom and the top, and we said from our constraint number 1 the solution is only at the bottom of the conduction or of the band. Now, despite all these three limitations we have seen, we can at the same time try to take some assumptions in order to make that evaluation of that integral very simple. The first one is from our Fermi function here, we should assume that E minus EF is much greater than this KT. And if that happens, it means this exponential of this function is very much bigger than 1, which means we will now neglect the 1. And if we make that assumption, it means our Fermi function, f of E, is now just equal to exponential minus into E minus EF all over KT. The 1 is neglected. So after that, then our integration will now be reduced to this. That is N of E is equal to Cc, which is the concentration of electrons in the conduction band, and we are now going to integrate it from Eg, which is the amount of the energy gap, to the infinity of E minus Eg. We already define E as the energy applied. Eg is the what? The band gap energy, raised to power half, then exponential of this much. That is what we already have here after taking this assumption and simplifying our Fermi function to this. And the moment we do that, we will now say X is equal to this much, that is E minus Eg all over KT. That is, we are replacing these ones by a variable E. And if you do that, our integral should now reduce to this. This, our Cc, is here, and then from here you can see that if we say X is equal to this over this, it means you can make this KT the subject. And if you do that, you end up getting KT, where E minus Eg is gone by replacing it with this X. Because here you can see I have X raised to power of half, which means from here E minus Eg is equal to X times what? KT. You can see that E minus Eg is raised to power half, which is a square root. So it means the square root of this will be square root of X and what? KT. So my KT come out and my X goes in, because we are differentiating with respect to it, and integral of everything here. Now if you go to some standard integration tables, you find that the integral of this, you can see that X raised to power half exponential minus X, it is integration by parts, and the essence of this course is not to show how to integrate. So from standard integration table, this is given by a half square root of pi if you take this limit from 0 to infinity. Now if we do that, finally our Ne, which is the concentration of the electrons, will be equal to Nc exponential this, where our Nc is given by this, that is 2 into 2 pi m asterisk subscript EKT all over h square, everything raised to power 3 over 2. And if you want to do the same analysis for the whole, you find that NH instead of Ne takes similar form, that is NV exponential minus EF over KT, and our NV is given by this, just like NC given by this. We have defined all these terms. Now with this, we go to the next topic, that is the electrons and the holes mobility. As I told you from the beginning of this lecture, the essence of production of semiconductor materials is for them to be used for conduction of electricity, to construct or to develop electronic system, and we introduce foreign materials into them in order to regulate the amount of charge they will carry at a particular time. Now this electron and the hole, they have mobility, which are given by mu. If you see mu n, it is for the electrons, negative, and mu p is for the holes, which is positive. They are the measure of how fast the drift velocity of electrons and the hole is when a field, electric field intensity, is applied to them. And it has been discovered that for the silicon, the conductivity of electron is 0.135, meters square per volt second, and that for hole is 0.048. And for germanium we have 0.39, for electrons 0.19 for holes. Now from here we look at another parameter which is a determinant of the conductivity in any semiconductor, that is the resistivity, because we know the conductivity of a material is 1 over the resistivity. So this resistivity is determined by using the mobility we have just seen, and also the charge carriers, that is either hole or electrons, and of course we look at their concentration. And the formula for resistivity is given by rho equal to 1 over Ni. This is what we call the intrinsic concentration, that is the number of bonds that have been broken to produce pair of electrons and hole. If 1 million electrons are produced, we have 1 million holes because it is intrinsic. And Q is the charge of an electron, which is 1.6 times 10 to the power minus 19, and the mu n and mu p, they are just what we have discussed here. They are our mobility for the hole and for the electron. Now, as I have already told you, the conductivity is reciprocal of resistivity. Now we want to see the formula for calculating the conductivity with respect to temperature, because whenever temperature changes, the number of charge carriers created is also changing, and of course the energy they have for them to move from the valence band into the conduction band also change. So there is a formula relating the conductivity to the change in temperature, and it is given by this sigma equal to sigma naught. This sigma naught, it means it is the initial value at the initial temperature, exponential minus Eg. We know this Eg is the energy gap, all over 2kT, where K is the Boltzmann constant and T is the temperature we are talking about. So from here we can see the conductivity sigma is related to the temperature inversely, but though it is related to its exponential, but inversely, because the temperature is at the denominator. As we have said, Eg is the energy gap, T is the temperature, and the K is the Boltzmann's constant. This time its value is equal to 8.62 times 10 to the power minus 5 electron volt per Kelvin. Now let us look at a worked example to illustrate how we can use this formula for calculation. The question says the electrical resistivity of pure silicon is given by 0.46 ohm meter at the temperature of 300 Kelvin. We are now asked to calculate the electrical conductivity at temperature 25 degrees Celsius, and the energy gap is given to us as minus 1.1 electron volts. Now if we use the equation we have just seen, this equation of conductivity in related to the temperature, we have we substitute the value of the temperature, initial temperature, which is said to be 300 Kelvin. So I'll say sigma of 300 Kelvin is equal to sigma naught, the initial, exponential Eg over 2k times 300, which is the temperature. Then we also find the expression for this conductivity while the temperature is 425 degrees Celsius, which must be converted into the what? The Kelvin, by adding 273. That will give you 698 Kelvin. Now if I substitute in that formula again, I will say sigma of 698 is equal to sigma naught exponential minus Eg all over 2k times 698. Now I have two equations, and I can see equation 2 divided by equation 1. If you do that, you will be left with this, that is sigma 698 all over sigma 300 is equal to sigma naught this all over sigma naught this. These sigma naughts will now cancel out. I will be left with exponential this over this, and you know, if I have two exponentials, I will take one and subtract the exponent or the power of the other one. So I will say now minus Eg all over 2k times 697 minus that of the denominator, which is minus Eg all over 2k times 300, which is our initial temperature. Now if you do that, you can see Eg minus Eg is common, and 2k at the denominator is also common. I factorize them out. I will be left with exponential minus Eg all over 2k now times this much, that is 1 over 698 minus 1 over 300. And if I cross multiply from here, I will say sigma 698 is equal to sigma 300 times this much. And I am already given the value of this sigma 300 from the question, which says is 0.46. So I'll now substitute it here. 0.46 times exponential of everything here. My E, G is given by 1.1, and my 2K, 2 is constant, K is given by 8.62 times 10 raised to the power minus 4. So if you evaluate everything here, you end up getting 17.4 per ohm meter as your conductivity. So we now look at the equilibrium condition when we have semiconductors which are fully compensated. Which semiconductors are said to be fully compensated? They are the ones that are under complete ionization, where Na and Nd are equal to 0. What we mean by this is that whenever temperature rises, we know electron and the hole pair is created in such a way that the bonds are being broken. If 1 million bonds broken, we know we have 1 million electrons and equivalent 1 million holes. Now, in a situation where it is fully compensated, you see that the number of electrons will now be equal to the number of holes, so that they will cancel one another. This is what we call compensated semiconductors. So in that case, our N0, which is the concentration of electrons, plus the number of the acceptor atoms, that is group 3 elements, is equal to P0, which is number of holes, plus the number of what? The donor atoms, which is Nd. And we know from the initial that the product of N0 and P0 is equal to Ni square, which is the intrinsic concentration. Now, if I wish to make my P0 from here the subject, the P0 should be equal to Ni square all over N0. So I will substitute it here. So N0 plus Na is equal to Ni square over N0 plus Nd. If I multiply through by this N0, I will be left with N0 square minus, that is after rearrangement, I have Nd minus Na times N0, then minus Ni square, which is the intrinsic concentration, equal to 0. So this is a quadratic equation because my N0 here has a power of 2, and here it has a power of 1, and here it has a power of 0. Let us remember our quadratic equations from the basic maths of secondary school. Now, if I use the formula which says minus b minus plus or minus b plus or minus square root of b square minus 4ac all over 2a, if you do that, your N0 should be equal to this. That is Nd minus Na all over 2 plus square root of Nd minus Na over 2 square plus Ni square. This is the expression for the majority charge carriers N0, because we introduce donors, that is group 5 elements. So if you understand this in a similar way, we can find the concentration of the holes when we have p-type semiconductor. That is when we introduce group 3 elements. And the same analysis will give us this formula. P0 is equal to this. If you look at it, they are the same, only that here is P0 and the other one is what? N0. Wherever I'm dealing with N, I have Na minus Nd. But here, where I'm dealing with what? P0, I have Na minus Nd. So from these two formulas, we now move to what we call the drift currents. That is the amount of current that will flow in any semiconductor whenever electric field is applied to it. Now, these charge carriers, as I said, whenever energy is applied to them, they will start moving. And if electric field is constant, we should assume that the velocity of these charge carriers during their movement is supposed to be constant, but in reality that's not the case, because we have problem of collisions where one electron will collide with one another, thereby cancelling or reduces the speed with which they are moving. So the amount of current density, that is current per unit area, whenever a field is applied to them, is what we call the current density, J. And this one is for the P, that is for the holes, is equal to E, charge of electron, mu P times P times E. where mu p is the conductivity mobility of the holes, P is the concentration of holes, and E is the electric field applied. In the same manner that for electrons is given by this. Instead of mu P here we have mu N, instead of P here we have N. So if you want to find the overall amount of this current density, you add that of electron to that of a hole. That is this one for the holes, you add it to this one for electrons, and you end up getting this. And from here you can see E is common and capital E also is common. And if you factorize it out, though we didn't do it there, we can have E small times E capital into mu N times N plus mu P times P. Now with this formula, let us take a typical worked example. Here we are asked to calculate the draped current density of a germanium, which is at 300 degrees Celsius, which is the temperature, and ND, the donor as atoms, is equal to 0, which means it is not N-type, because here we have acceptor atoms equal to 10 raised to the power 16, which means it is P-type semiconductor. And Ni, that's the intrinsic concentration, is given 2.4 times 10 raised to the power 13, and the mobility of electron and that of holes are given respectively. So the set which you calculate the current density under the field of 500 volt, 50 volt per centimeter. As I have said, the semiconductor is a p-type, so I'm going to use this formula, the one we have derived here, that is the p naught. And that formula, if you look at it, I have everything, because Na is equal to 10 raised to the power 16, Nd is equal to 0, and Ni, that's the intrinsic concentration, is given here as 2.4 times 10 raised to the power 13. So after substituting everything, you end up getting your value of P is equal to 10 raised to the power 16 per cm cube, which means we don't need to even use the formula. Even if you use it, you are going to end up getting 10 raised to the power 16. And then if I want to find the concentration of the minority, because this is a p-type, so electrons are the minority, so I will use the formula for intrinsic to say N is equal to Ni square all over P. The Ni is given as 2.4 times 10 raised to the power 13, and my P is given also times 10 raised to the power 16. So finally I got 5.76 times 10 raised to the power 10 per cm cube as the concentration of electrons, which are the minority charge carriers. Now using that value, I'll use the formula for calculating the total current density, that is E times capital E into mu N times N plus mu P times P. My E is the charge of electron, is given here 1.6 times 10 raised to the power minus 19, and electric field is given as 50 volt per centimeter, and the mu N is given as 3,900 if you look at the question, mu N, and this is mu P, 1,900. And the number of electrons I just calculated here as 5.67 times 10 raised to the power 10. So substituting everything here and evaluating, I got 152.002 ampere per centimeter square, which is our overall current density. So ladies and gentlemen, thank you very much for being with us. This is the end of this lecture number 5. Thank you.